All right, so first off, I need to find the derivative. So we have v equals IR. It is a little toasty. All right, so we have a product of two variable quantities here, the I and the R, and v itself is variable depending on what I and R are. So we're going to have to take the derivative of this, but it's going to involve product rule. So dv dt is going to be equal to the derivative of I times R. So first is I times the derivative of the second, dr dt, plus the second, which is R, times the derivative of the first, which is di dt. That's all A is asking us to do. And it seems like it would be a lot more difficult because it really seems like it's asking us to find three unique derivatives. But all we're looking to do is relate these three derivatives to one another. By taking the derivative of v equals IR, we've accomplished that. Right, so we have a relationship between those three derivative quantities. So that's good news. Suppose that the current is increasing at a rate of 0.3 amps per second while the resistance is holding steady at 4 ohms. Right? How quickly is the voltage increasing across the resistor? Right, so this is where a little bit of interpretation and maybe referring back to the original setup comes into play, especially if you're not familiar with this concept. So again, the current is increasing at a rate of 0.3 amps per second. Right, so just going back, current is measured in amps, right? But current is abbreviated with I, right? So the I represents the current. So what they're telling us is that di dt is equal to 0.3, all right? So I might make a note of that just off on the side, and by might, I mean definitely. So di dt is equal to 0.3 amps per second. All right, the resistance is holding steady at 4 ohms. All right, holding steady, what does that say about the rate of change? Constant rate of change is 0, so dr dt is equal to 0, but R itself is going to be equal to 4 ohms. 4? Yeah. Actually, I shouldn't try to squeeze it in there because it's going to look like 40. All right. So it seems like they didn't give us enough information, but it turns out they gave us the perfect amount of information. They didn't tell us anything about the amount of current that's accounted for here, but since dr dt is equal to 0, that's going to be irrelevant anyway. Right, so I could do my substitution, and that's going to be, I'm going to bring it in. I'll just write it as I, even though it's irrelevant, times 0 plus 4 times 0.3. Okay, so we're looking at 1.2. Then the question becomes 1.2 what? You can go back to the units that were given in the problem. They told us that voltage is measured in volts. So we can get it from there, and we can say volts per unit of time, so volts per second. Right? Another way to handle it would actually be to just kind of along the side, or alongside of our calculations here, just take note of the units. So I could just do that really quickly. The current is measured in amps. The resistance per unit of time, bless you, is measured in ohms per second. All right. Then, again, resistance is ohms, and the current itself, as you know, it's measured in amps, but as a rate, amps per second. So with either one of those, you're going to get appropriate units. All right, so all of this boils down to the idea that this would be measured in amps times ohms. I put a little extra wiggle in my H for some reason. Per second. All right, so that could actually be your units for your final answer. All right. Now, just going back to the idea of a volt. Right? So a volt is the product of an ampere and an ohm. It kind of makes sense that in our derivative, we're looking at the product of amperes and ohms. Right? So it's just what happens is it was determined that we're going to call these volts by definition. So we end up with the units of volts per second. Right? The moral of the story here, though, is the idea that you don't actually need to know the names of the units. Right? Like, let me see if I get this right. Kilogram meters per second squared. It's a Newton, right? Okay, good. All right, I got it right. Right? I know it as kilogram meters per second squared because I do the math, I do the calculus, and that's what the units turn into through the derivative process. The fact that somebody threw their name on it, that doesn't mean anything to me. Right? So you would know it as a Newton because those are the measures associated with force, but I know it as kilogram meters per second squared. Right? So. Yeah. Yeah, the first person to get to something gets to name it. So, although, you know, a lot of the concepts that Newton got to name, I'm pretty sure he had nothing to do with, but, you know. Apple Falls, it was like, all right, just name everything after me. Cool.
So I want to be.
Yeah, you kind of luck into a circumstance. Yeah, that's kind of the way we want life to work. All right. So, how quickly is the voltage across the resistor increasing? 1.2 volts per second, or 1.2 amps times ohms per second. One obviously involves writing more stuff. All right. Now we're switching it up a little bit. Still working off the same derivative. Technically, this was part B, right? So let me make a note, because the actual substitution was your part B. All right, so the voltage across the resistor is held constant at 20 volts, while the resistance is steadily increased at a rate of 0.4 ohms per second. What's the current through the resistor when the resistance reaches 10 ohms? All right, so working off the same derivative, we have some other circumstances to take into account here. All right, so again, I'm just going to off on the side here, just take note. All right, so we have voltage is 20 and it's being held constant. All right, so I'm just going to kind of cordon this off a little bit. So our voltage is 20. But it's constant. While the resistance is steadily increased at 0.4 ohms per second. All right, so dr dt is increasing at a rate of 0.4 ohms every second. What is the current? So we're looking for I when the resistance reaches 10 ohms. So we'll have an R value of 10. All right, so we go off again with our derivative model. So dv dt is equal to, it was I times dr dt plus R times di dt. All right, left-hand side is going to be equal to 0. They told us that. All right. I is currently unknown. dr dt is 0.4. R is 10. We're looking for di dt. So you look at this and say, oh, we don't have enough information to solve the problem. But we actually have enough, because if you go back to your original model, V equals IR, right, 20 is equal to I times 10, making I equal to 2. Okay, so 2 amps. All right, so now I can pop that bad boy in. And solve. All right, so we're looking at di dt is equal to, would be, I'm subtracting and dividing, so negative 2 times 0.4 over 10, which I'm gonna, sorry, I'm gonna try to be fancy now. Just gonna tuck in a little calculator action here. You can't see it on the big screen, but in the video it's going to look gorgeous. All right. So negative 2 times 0.4 divided by 10. You got negative 0.08. All right. So negative 0.08. This would be amps per second. Right. Yeah, I don't know if it was necessary to actually hit record on that, but I'll see in a little while, I guess.